In this video, I wanted to take a moment to go over how I solve force of friction problems in physics. Before we get started, though, I wanted to take a moment to review a little bit of Newton's laws, because Newton's laws, really, our understanding of those laws and the relationships presented in them help us to problem solve through these calculations. So I'm going to use our CAMI document, and I added a page at the end just for some quick notes as a review. All right, so Newton's laws. All right, first law is called our law of inertia. And our law of inertia looks at how objects behave when forces are applied or forces aren't applied. And so we can describe an object as experiencing what we call balanced forces. And that's where all of our forces that are acting on our objects, so when I say all of them, I'm talking about forces net, or our F net. When they're added together, they add up to zero. And so we have zero net force. And we can tell by observing an object if it's experiencing zero net forces, because we'll notice that it's at rest or it's experiencing constant motion. If those forces are unbalanced, then that means our F net is greater than zero. That object is accelerating. Our second law is the relationship between force, mass, and acceleration. And so that's where we have force equals mass times acceleration, or more specifically, F net equals mass times acceleration. So we can use second law when we have a situation like this one, where we know what the F net is, we know what the mass of our object is. We can actually find out what the acceleration looks like. So we can use Newton's second law to find that missing piece. With F net equals mass times acceleration, it just tells us the relationship between force, mass, and acceleration again. So let's say that we rearrange this and we look at the equation like this. So how this can be interpreted is when an object undergoes a greater force, the acceleration is also going to increase. If we decrease the force on an object, or the F net, that object will also experience a decrease in its acceleration. That's assuming that mass is constant. We don't change the object at all, and that typically happens. The third law looks at action-reaction. And so what that deals with is two separate objects. Okay, I have two separate objects. Let's pretend like this one is a hand and this is a ball. I like to make simple pictures when I'm doing this. And let's say the hand hits the ball. Well, if the hand hits the ball, then the ball also hits the hand. That's what action-reaction means. So if I'm going to do a little free body diagram, there's a force vector to represent the force that the ball experienced from the hand. And then this vector would represent the force that the hand experienced from the ball. And they're going to be equal and opposite. That's action-reaction. So just a quick little review of those. It's always good to keep in mind the things that we know, so that when we try to solve a problem, we can remember that our toolbox has a lot of stuff in it. We just have to remember what all our tools are. So in this first sheet, we're just getting more specifically into the types of friction, and those are forces. So I'm going to solve question number 1 and question number 5 for you. So in question number 1, we asked you to draw and label the free body diagram for each of the situations here presented. We asked you to include the force quantities and to calculate F net. All right, this is a good first step in solving any force diagram problem that you might be presented with in physics. Always start with a free body diagram. It allows you to illustrate, to visually see all of the forces and how they're going to interact in a situation on an object. So in this first one, we have a 2.18 kilogram book. It's sitting on rest on top of a table. So there's a lot of information there. We know the mass of the book, and we also know that it's at rest, and that's really key. We got to think of Newton's first law. If I see that it's at rest, I know that I have balanced forces acting in this situation. And that's something I got to keep in mind when I'm drawing my free body diagram. So as usual, when I draw a free body diagram, I keep it simple, and I always start with a square or a rectangle. And I draw a circle to represent my center of mass. And I know that this book is just sitting at rest on a table, so there's only two forces that are acting on it. We have a force of gravity, because it acts on everything. And then because it's at rest, it's in contact with a surface, there's an opposite force acting up that we call the force of normal. There are not any forces acting horizontally. They have not been described in the situation. There is no applied force being described, so the only ones I can assume that are there are going to be the force of gravity and the force of normal. I know this object is not moving at all, so these two must be balanced. So usually I have little hash marks like I do in math class to show that. And I know the mass of the book, so I can actually go further and I can actually label what these forces really are. So I'm going to start with the force of gravity. So force of gravity equals mass times acceleration, and it's specifically acceleration due to gravity. So I put that little g there just to remind myself that it's a specific one. I'm going to plug in my numbers. The mass of the book is 2.18 kilograms. Now it's important that it's in kilograms. If you are taking the mass off of a scale, usually scales measure in grams, so you have to do a conversion. And then acceleration due to gravity is negative 9.81 meters per second squared. All right, so plug that into my calculator. I consider significant figures based off of my mass, which has 3. So my final answer for this is going to be 21.4 kilogram meters per second squared. I can't just make up units. I have to use what I have. But I have to remember that 1 Newton is the amount of force required to move a 1 kilogram mass at a rate of 1 meter per second squared. So a kilogram meter per second squared is the same as me saying a Newton. So I can change that over to newtons, and that's okay. I haven't made up that unit. It came from the other ones. It's been derived. And I know this is negative because that was negative. So I can start plugging in some numbers. Okay, and then I know this one is positive 21.4 newtons because it's acting in the upward direction. And the last thing I should do is calculate my F net. So I know, I'm going to change my color here so that it just shows up a little better, that F net is the sum of all of the forces. So the only forces I have here are Fg plus Fn. So Fg is going to be negative 21.4 plus positive 21.4, which equals 0 newtons. And that's awesome because I know that it's at rest, so I know that I did everything correctly. All right, so that's just filling in what I know. And as I go down to the second part of this worksheet, I'm going to always start with what I just did in order to solve the problems that I'm working on. All right, so let's head down. And the next problem that I'm going to do for you is going to be number 5. So in this problem, let's read the problem first. It says it takes a 50 Newton horizontal force to pull a 20 kilogram object along the ground at a constant velocity. What is the coefficient of kinetic friction? All right, so I know I have the force that's using to pull the object. I have, right there, I have the mass of the object. I know it's moving at a constant velocity, and I'm looking for the coefficients of kinetic friction. All right, so it's always important to think about what I know and what I'm looking for. I know from what I've learned during the lab this week, as well as the information presented at the beginning of this worksheet, that in order to solve for the coefficient of kinetic friction, I need to know what the force of friction is and the force of normal. All right. So neither one of those is given to me directly in the problem. So I'm going to start with a free body diagram and see if I can figure out what they are. So step number one is always free body diagram. So FBD, draw your free body diagram. So I'm going to start with my picture. All right, there's my object, whatever it is. I know that it is experiencing a force of gravity because everything does. I know, so that's my force of gravity. It's in contact with a surface, so it's going to be experiencing a force of normal as well. The problem tells me that it's experiencing a horizontal force that's pulling it, so that's a force applied. And it actually tells me that that is 50 newtons. And all objects that are in contact with a surface are going to, and moving, are going to experience a force of friction opposite to the direction that they're moving. So I know there's a force of friction going this way. And because it's moving at a constant velocity, I know that these two must be equal. So this is a force of kinetic friction because it's moving. So that's 50 newtons. All right, what I don't know right now are the magnitudes of the force normal and the force gravity. So I'm going to solve for those. Just resolve for all of the forces that I can. Okay, so I'm going to look for force of gravity. And I know this is mass times acceleration due to gravity. My mass is 20 kilograms. Acceleration due to gravity is negative 9.81 meters per second squared. I'm going to plug that into my calculator. I'm going to use sig figs and realize I only have one sig fig. So my answer actually can only be one sig fig big, which is not the best way we like to do it, but that's what our answer is going to be, is 200 newtons. So I know that it's experiencing a force of gravity that's 200 newtons. And remember, that's negative because it's downward. So I could fill that in here, 200 newtons. Now I can put the negative here. I don't have to because the vector's pointing downward. So the direction's already been illustrated. Sometimes I put it there just to remind myself though. And it's the same thing for the plus sign. It's not necessary because the arrow's pointing up, but it's just there to kind of highlight the fact that they're opposites, but they're equal. All right, so now I've filled in all of those forces and I'm going to try to solve my problem. So I know that the coefficient of friction exists in a formula given above that looks like this. All right. And I know, because I learned Algebra 1 in 9th grade, that I can rearrange this to find the coefficient of friction. And it would look like this. On my free body diagram, I have the force of normal. I figured out what that was. I have the force of kinetic friction. So I can just plug those into my calculation and figure out what my coefficient of friction is. So my coefficient of, or my force of friction is 50 newtons. My force of normal is 200 newtons. Plug that into my calculator. Both of these will cancel, which that's good because coefficient of friction does not have units. And the answer that I get is 0.3 is the coefficient of kinetic friction for this particular object. It has no units. And I feel like I'm in the right spot because the final number, the coefficient of friction that I ended up with, is somewhere between 0 and 1. And that's where a coefficient of friction should be, to be correct. Hopefully this helped. As you move on to the other problems, always start with the same method. Free body diagram first. Fill in all the forces. Try to solve for the ones that haven't been given to you directly. And then go ahead and solve your problem with what you have. If you have any questions, just let us know.